Okay, thanks so much for coming this afternoon. It's really a pleasure to be here with so many alumni of this great department, and we really appreciate you coming, and also again we appreciate the invitation from Pate Dawson to use their facilities for this. So thank you all, and I hope to talk to you today a little bit about where do we flow from here in terms of getting water for the state of Texas, and I have some ideas I'd like to share with you in this regard. So just to give you a little background, the point of this slide is there's not very much fresh water in this world. Only about 2.5% of all the water on Earth is fresh water, and 2/3 of that is locked in glaciers and ice caps. Of course, those are melting, so that number is going to change in coming years, unfortunately. The renewable annual supply, in terms of what falls as rain and whatever, is what looks like a huge number, but it's only a tiny, tiny fraction of the water on the Earth. And 2/3 of that is kind of recycled through evapotranspiration, which means only 1/3 of that tiny fraction is really available for us for water withdrawals. So even in the best of times, water is scarce. It's easy to find what the latest status of the Texas drought is. And dark red is very, very bad. Red is only very bad. And you can see that a major part of Texas, not nearly as bad as it was 18 months ago or 24 months ago, but we still have some serious problems. And there's problems right here just to the west of where we are sitting today with the problem. And so the Texas drought continues, and there's no relief in sight. The status of reservoirs as of this month is also not good. There's plenty of water in the east of Texas. The blue is good, means the reservoirs are 90 to 100% full. But here's Lake Medina, which is in the very red, in the 0 to 10%. I say in here 3.6% full. And Lake Travis, which is important to us in Austin, is 36% full, which is a little better than last summer when it was down around 32. But we have a long way to go before we have. So this is a problem, and it's not going away. And so we have to ask ourselves, where are we going to get water as the population continues to increase? So this is kind of all the possibilities for where we might find water. Conservation, both direct and indirect, and I'll talk about that for a bit and tell you what I mean by that and what we can do. Municipal stormwater and rainwater harvesting, which I put together here because a lot of the ideas are similar, even though they're often dealt with somewhat separately. New surface water reservoirs, new high-quality groundwater supplies. I'm not going to talk about either of those because I don't think they exist. I don't expect that we're going to be making any new reservoirs, or at least not very many. In the United States, we're taking dams away and destroying reservoirs rather than building new ones. I don't think it's going to happen in the state of Texas, or at least not in any substantial way. I don't think we have any groundwater supplies that aren't already tapped, and in Texas, over-tapped. So I don't expect that to happen. And then we have the possibility of desalination, both seawater, which for us means the Gulf, and brackish groundwater, which there's a lot of in Texas. And then the possibility of direct and indirect potable reuse of wastewater. So this is basically an outline of my talk. I'm going to spend several minutes talking about conservation, just 1 or 2 slides on municipal stormwater and rainwater harvesting. Nothing at all about these middle things because I don't think they really exist. I've done quite a bit of work on desalination. I'm going to bore you with some research slides on that, and then just 1 or 2 ideas on direct and indirect potable reuse. So that's where we're going today, and hopefully I won't take up all the time, and we'll have plenty of time for questions. So, the first item that we can think about is direct water conservation. I want to start with this because it's the one thing that every individual can actually participate in and make a difference on. And so, by personal choice, you can save water by watering your lawn less frequently or not at all. Or you can, xeriscape your lawn so that you are not using water in the same way. Showers use less water than baths generally. Not running the water while you're washing your dishes or brushing your teeth, these things actually make a difference. and of course not washing cars. In Austin, you're not allowed to wash your car anymore. The only way you can wash your car is to have it done at a commercial establishment, and they probably don't want that to happen either, but you couldn't shut those businesses down. There's also ways in which by engineering design we save water, and this is kind of interesting. Toilets in the 1950s and 60s used about 7 or 8 gallons per flush. Then around 1970, they went to 5 gallons per flush. Virtually all toilets that are put in houses and businesses these days are 1.6 gallons per flush, and there's new ones out that are 1.1 gallon per flush. It turns out that the average person flushes the toilet 5 times per day. And so a family of 4, if they have a 1.1 gallon per flush rather than a 5 gallon per flush, it's saving 3.9 gallons per flush in the course of a month. That means over 2,000 gallons of water, which is a substantial amount of water and actually makes a huge difference. And toilet flushing is the single highest use of water in a household. So if you haven't gotten around to changing your toilets to a 1.6 gallon per flush thing, I'd recommend that you think about doing that. And then, of course, there's also low-flow shower heads and faucets, which also, in time make quite a bit of difference. It turns out that all large cities in Texas, despite the increase in population over the last 10 years, have reduced their per capita water flow quite substantially. And I'll show you a slide about that in a minute. It turns out that there's also a lot of water that can be saved in industrial situations. And this is very kind of site-specific. But I just wanted you to note that 10 years ago, the 5 largest water users in Austin were 4 semiconductor manufacturing plants and the University of Texas. And all of them have gone through a substantial process to reduce the water usage. And I was involved with one of those semiconductor plants doing an extensive, what I call here a triage analysis to go through. They had hundreds of uses of water in their plant. And we with a graduate student, we looked at every single one of them and looked for the possibility of reuse of that water based on the quality of the wastewater as well as the volume of that wastewater. And then we started working with them on using the ones that were the highest possibility for recycle and saved a substantial amount of water in that plant. This is the graph of water use in the 6 largest cities of Texas. From 1985 to 2012 on the basis of gallons per person per day. And you can see all of them have a downward trend line. I have to congratulate San Antonio. The green line here, they were way ahead of the game of everybody else. And they're very, very good in terms of not using a lot of water. But you can still see that it's in the range of 140 gallons per person per day, which of course includes all the industrial use and the entire use of water in the city. But that number could still be reduced probably substantially again. Austin, which I hope you care about since you graduated from the university there, is the blue line here. And you can see we weren't nearly as good as San Antonio for a while, but now we've kind of caught up. It's a good graph. It shows that we've made a lot of progress. And again, when you account for the fact, well, this is per capita, but we're actually using less water in Austin and in San Antonio, even with the rising population. This university has done a major job in trying to reduce its water use. There's lots and lots of details about this that I won't bother telling you about, but they have a huge amount of irrigation that goes on to keep the campus beautiful. And they went through this process in 2011 to make all these changes, or many of the changes. And you can see that in 2012, their consumption of water was 66% lower than the previous year, which is an amazing amount of saving. And mostly was because of these irrigation changes, although they actually made changes in, throughout the university with low flush toilets and shower faucet heads in bathrooms and whatever that were changed. So a lot of work has been done in that. This is up to date. The Austin water usage is 3 years shown in here. They show a dry year, which is this high value of 2011. And it was really in October of 2011 that people began to realize that the drought was really getting serious, and there was a substantial drop in there. This other line here is a wet year. You can see there's a lot less use in the summer. And this is where we are in Austin this year, 2015, which is considerably lower than before. So water savings, water conservation can really mean a lot. It turns out that in Austin, there's so much less use of water that the utility doesn't have enough money. So they've actually had to go to the city council and ask for a change in water rates because people are saving much more water than they had originally anticipated when they set the rates. So that's not necessarily a good thing. I mean, this water savings is a good thing, but the utility not having enough money to run the plants is not a good thing. But it is interesting to see how that can happen. The second thing I wanted to talk a little bit about indirect water savings and water conservation. And it all has to do, or what I'm talking about anyway, almost all has to do with the fact that energy use and water use are closely related. Because we use a lot of water to produce energy, mostly for cooling towers, then we also use energy for water in treatment and distribution and also in heating. So it turns out that these things are much more closely related than you might expect. So this is just two graphs of Texas. On the left we have the generation capacity in kilowatts, and on the right we have the water consumption in gallons per kilowatt hour. And you can see, just visually, there's a one-to-one correspondence between those things. And so it turns out that production of energy takes a lot of water. And it turns out that the distribution of water takes a tremendous amount of the energy. So this is energy used for drinking water, kilowatt hours per million gallons. Treatment is only 15% of that, and the distribution of water throughout a city is 85% of the energy that's used for water. And of course, that can be more in some situations. And wastewater treatment actually takes quite a bit of energy. The typical plant uses activated sludge, uses about 1,300 kilowatt hours per million gallons of wastewater. If you do nitrification, it's even more, and if you do advanced treatment, it's even more. And of course, these days we're trying to get to these higher levels of treatment, and so we're using a tremendous amount of energy per million gallons of wastewater. And so the idea is that if you use less water, you'll have less wastewater and therefore less energy use in here, and then you'll have the additional water savings from that. So the point is that saving water saves energy, and saving energy saves water. And the conserving water saves energy needed for treatment and distribution as well as for wastewater treatment directly. And conserving energy saves the water that's needed for cooling during the electrical generation. So if you turn out your lights or you replace your light bulbs with LEDs instead of incandescent bulbs, you're saving water as well as cost of electricity. Okay, so that's it on conservation, and let me talk just a tiny bit about rainwater harvesting and municipal stormwater. So I think the old paradigm for municipal stormwater was to get it downstream out of the city as fast as possible, and that required building some pretty large flood control projects, or making sure you had substantial drainage projects to have that happen. And you basically put in curbs and gutters to make sure the water flowed into those drains. But the new paradigm that hasn't really taken hold in our society, but I think should and probably will, is that you capture and use the water for irrigation or other use where it falls. And this is a tremendous paradigm shift, and would affect every neighborhood in a city like San Antonio or Austin. You'd have to limit the impervious cover. You could think about making rooftop gardens on flat industrial buildings, of which there are many. And you might build many small water retention facilities so that the water would stay in the neighborhood and then gradually get used in that neighborhood for irrigation or whatever. And instead of trying to do curb and gutter and get rid of the water, you'd actually put breaks in the curbs to let water flow into the parklands or lawns or whatever. And this can make a big difference. And I just thought I'd show you a picture. I have an editorial remark here about rainwater harvesting. I don't know if any of you are thinking about doing that in your homes, but I really discourage you from using harvested rainwater as your drinking water source. It might be necessary in some places in the hill country and things like that, and that's all well and good. But you have, excellent drinking water in the cities of Texas, and I believe it's just much safer to use those as your drinking water source. Harvested rainwater can have a lot of contaminants in it that can make you sick tomorrow or 10 years from now, and I really don't expect people to do the kind of treatment that's necessary to make that water safe. So, as I said, this is an editorial. I thought it would be fun to show you this picture. This is the roof of the civil engineering building at Seoul National University. This is a garden that's been planted on the top of the roof. Of course, before they did this, they had to check that structurally it was okay. This is the brainchild of a former PhD student of mine, Mu-Young Han. He goes by Mu-Young. That's what the My is for. He calls this My Garden, but it's Mu-Young's garden. And this is, in fact, the civil engineering building at Seoul National University. And his vision is to have this kind of thing done all over the city of Seoul, and for that matter, all over the world. And in Seoul, it's really critical because they get a fair amount of rain and they have tremendous flood problems. And if they could actually capture the water on the rooftops, that'll be there. And I don't know if any of you have ever visited Seoul, but it's a concrete jungle. There's 20 million people that live in Seoul, and rainwater is a big issue, and flooding is a big issue. And this would be a way to think about that solving it. So I'm proud of my PhD graduate a number of years ago to come up with this idea. Okay, so I want to talk some about desalination, which I've done a fair amount of work on, and I just want to highlight a couple of the things that we've done in our research, and then try to kind of make it make sense in terms of water conservation. So seawater has between 30 and 45 grams per liter of total dissolved solids, mostly sodium chloride. Okay. But various other ion constituents as well. Brackish water can really be anything less than that, but typically we think about using sources that are in the range of 10 grams per liter of dissolved solids, which is considerably less, and therefore the job of desalination, getting rid of those ions, is less severe. There's a difference in how you do desalination or what you can expect for desalination in these. In seawater, of course, you're talking about coastal plants. The recovery, which is the fraction of the water you bring into the plant that you actually get to use as, say, drinking water. So that recovery is in the range of 30 to 50%. And typically, the concentrate disposal is to just dump it back in the sea. This is actually somewhat controversial in California right now, which is in one of the major cities in California is thinking about doing desalination in a major way. And people are wondering whether it's really okay to put that concentrate back in the sea. And by the concentrate, I mean, it's going to have all the salt in it. So if you get, say, 40% recovery, you're going to have 2.5 times the salt concentration in the concentrate than you started with, or at least approximately. And what happens if you put that back in the sea? Well, if you put it far enough out in the ocean, it's almost as close to an infinite sink as you can imagine. But if you put it near the coastline, it could have some real problems. And of course, if you put it far out, it's going to cost you a lot of money to do that. So it's somewhat controversial, but generally speaking, people think that putting it back in the sea is okay. But in brackish water, you're doing inland situation where you don't have the sea as a reasonable place to put the water. You do, because you have less dissolved solids in there, you end up being able to recover a much higher percent, 65 to 90%. Again, that's the water that you actually get to use versus what you put in. Somewhere in the range of 75 to 80%, in the middle of that range is really what's most common for this. And this is happening in Texas, in several places. But I should compare these recovery things to conventional drinking water treatment where you have a freshwater source where you get to use more than 99% of the water. There's only a small amount of sludge to dispose of in a typical drinking water treatment. So, but the real question for brackish water is, what do you do with that concentrate? Where do you put it? What do you do with it? And that's a question that we addressed in our research. So desalination is typically done by reverse osmosis. And this is a symbol that's used for membrane processes where you put in the feed water. What makes it through the membrane is the clean water, which in our case means drinking water, and the concentrate is the waste stream. And again, as I've indicated already, the recovery is the fraction of water that comes out as the permeate. So this is what a desalination plant looks like, a reverse osmosis plant looks like in here. They have, all these membranes are inside these pressure vessels. And each one of those has several of these modules. And inside the module there's a spiral wound membrane that looks like this. I'm not going to bore you with the details of how water flows through these things, but it takes a lot of pressure to put water through a reverse osmosis membrane. So what I want to talk about a little bit is the fact that desalination is really not so simple. And there are issues associated with the desalination process itself. There are issues associated with the post-treatment of the water, and we'll talk about that. There's issues associated with pre-treatment, and there's issues associated with concentrate. And I'm going to talk about each of these a little bit, and my own research has had to do with the pre-treatment and the concentrate management, and I'll say more about that. So within the desalination process itself, there is a thermodynamic limit of how much energy is the absolute minimum you can spend to get salt out of water. And the question is, how close can we come to that with good engineering to save energy in doing this process? There's been a lot of progress on this in terms of new membranes that have been used that reduce fouling and increase the flux, how much water you get through per unit area, per unit of pressure. And also, can you recover the pressure that you use for this? And there's been some very interesting work done on this to improve the existing systems. And without going into the details of that, I just want to show you how much progress has been made in this. In this graph, it's showing the energy usage in kilowatt hours per cubic meter for seawater desalination, where you're doing a 45% recovery, which is about the most that people think about doing. And this line here represents that thermodynamic limit. It's absolutely theoretically impossible to get below that line. And you can see that in 1970, when people first started doing this, this is about 1.5, and this is 12. So we were, what, eight times higher than the limit. And now we're about twice as high. So there's been a tremendous improvement in the use of energy for desalination. And so in 1970, people said, hey, it's impossible. It's just way too costly to do that in every way. And now, and this is the latest data I had, 2006. There have been some improvements since. Now it's somewhat reasonable. It's still a big use of energy, and it's still more expensive than other things, but it's not out of sight to do desalination. And this is for seawater, which is more expensive than brackish water. Post-desalination, this is interesting. It turns out that the water that comes out of reverse osmosis membranes is so clean that it's a problem. Okay? It's too corrosive to just put it in pipes, and it tastes terrible. I don't know if you've ever tasted distilled water or something like that. It's just like you want to spit it out of your mouth because it has no taste. Where does the taste of water come from? It comes from minerals. So, Coke and Pepsi, who make bottled water, and I guess we have Ozarka water here, which is actually, theoretically anyway, natural, but in the, Dasani and I forget what the Pepsi brand is, which are the Coke and Pepsi brands of bottled water. This is what they do. They do reverse osmosis treatment and ozone treatment and other things, and they make the water as pure H2O as they can. And then they have their own recipe for what they add back into minerals so that you can actually like the taste when you drink it. But if you do this for a whole city, then you also have to add minerals back in to make it taste. And also you have to add carbonates to adjust the alkalinity so that you don't corrode your pipes. It's conceivable in some cases you could blend with a small volume of the concentrate, but that would be very rare because the water quality probably wouldn't work very well. And you have to add polyphosphates for corrosion control, and you have to do disinfection. So there's a lot of work to do after desalination to make this work.
How come you can't blend with natural?
Well, because that concentrate is going to include some things that you don't want in the water as well.
About blending it
With other natural water, yes, that would be possible, as long as that other water quality is fine. Yeah. And so that would take care of some of these problems. Pretreatment has several opportunities or challenges. One is we have to control biofouling of the membranes. That would be not a good thing. So we have to do chlorination beforehand or ozone treatment beforehand. If you do chlorination, then you have to dechlorinate because the membranes can't handle the chlorine. There's particle removal processes which are typically important in there. And then the biggest problem in reverse osmosis membrane is precipitation onto the membranes, which is called scaling. And so you have to do some kind of scaling control to make these make sense. And I'm going to talk about a little bit of our research here on silica control in the next few slides. So it turns out the Rio Grande River, Rio Grande I guess we're supposed to call it, has a substantial silica concentration. And if this water you're going to desalinate that water, silica is going to limit what kind of recovery you can get. It also has a fair amount of calcium, magnesium, and alkalinity, which are important to us as well. So without boring you with all the details, we did a variety of tests to try to figure out what pretreatment would be necessary for this. We came up with various kinds of treatment where we're adding lime, we're also adding some magnesium, and we're also adding some sodium carbonate. This is to raise the pH and to precipitate several things. And as a result of this, we went from the raw water that had these characteristics of silica, magnesium, calcium, and alkalinity to much, much lower in all of these cases. And then we tested all three of these in this lab scale reverse osmosis unit, which is in the chemical engineering group at UT. And we came up with these results, which show, so this is a graph of the flux, how much water you get through per square meter of membrane per hour per unit of pressure in kilopascals. And we normalize the cumulative volume throughput. So this is how much water you get out in cubic meters of water per square meter of membrane. And if you didn't do any pretreatment, low is bad on this graph. It means you're not getting very much water out for the amount of pressure that you're putting in, and you have to stop with only not very much in there. And the best of these was that pretreatment 1, which showed that we could get only about 20% flux decline and recover 70% of the water, as opposed to the Rio Grande River, where we got more than 50% flux decline and could only get 30% of the water. So there's a huge difference that pretreatment would allow to happen in this case. Concentrate management is another area that I've spent quite a bit of time on, and again, the idea is here, what can you do with this concentrate? But this is the predominant problem in inland desalination, is what do you do with the concentrate? So our idea was to consider a treatment of the concentrate itself that would allow you to increase the recovery in further. So we did this in a couple of different ways. So here's the way this works. You usually have a few, 2 or 3 RO units in series. And you're taking the concentrate of one as the input to the other. And you're taking what passes through the membrane as your product water. And you usually put 2 or 3 of these in series, and then you have to throw out the concentrate. But we decided to use either electrodialysis or another system I'll tell you about as a way of recovering even more and adding to the product water. And the other way we did this besides electrodialysis was to have this scheme where we oxidize the anti-scaling, then precipitate in a separate unit. So rather than have scaling happen on the membrane, precipitate separately. Then do a solid separation to get rid of that precipitate, and then take that water and put it back into the next RO unit. And we did lots of things where we tried to do the anti-scalum oxidation, and that's measured here because of the anti-scalum had phosphorus in it, was how much phosphorus was released. And you can see that we did lots of different experiments, and I'll show you what they were about. in a minute. But some worked very, very well, and others didn't work nearly as well. And we're using a combination of hydrogen peroxide and ozone to do that oxidation. And I'm just going to point out that we did all these different conditions, and they all had different results. And the key is that all the top ones, which are good, contain calcium. And these ones, when you had both iron and calcium in there, didn't do so well. And all the ones at the bottom didn't have calcium. So calcium was clearly a key player in this. And then we did lots and lots of experiments to try to figure out why. And it turns out that this was, bottom line of this result, is that the calcium compound, the calcium could complex with the antiscalants, which is in the water, which is here, and change the conformation of it to allow ozone to attack this molecule. Very complicated to figure this out. And PhD student Lauren Greenlee, this was her work for the PhD. And the result of that is that you could improve the recovery of desalination substantially from in the range of 80% to perhaps 95 to 96% by doing that change. And that's a huge difference in terms of how much water you have to dispose of. If you have 80% recovery, you have 20% of water that you have to dispose of. If you have 95% recovery, you have only 5% of the water that you have to dispose of. So you've reduced that disposal problem by 75%. So it's not so much the value of the water, it's the saving of the disposal problem that makes this worthwhile. The second way we did it was with electrodialysis. And so in electrodialysis, it's obviously an electrical system. You have a cathode and an anode. You have all these membranes in the middle. You have a cation exchange membrane and an anion exchange membrane. You put water up through them all. And it turns out that in some cases, an anion exchange membrane, cations can't pass through, so they try to go toward the cathode and they can't get there, and the anions try to go to the anode and they can't pass through the cation exchange membrane, so they're trapped in there. But in the adjacent units, the cations can pass through the cation exchange membrane and the anions can pass through the anion exchange membrane, and you end up with clean water coming out the top. So you collect separate, that's not what I was supposed to do. You collect separately the clean water as the diluate and the dirty water as the concentrate, and you can use that diluate as product. There's also the production of gases, hydrogen on the cathode side and oxygen on the anode side, so that there's issues with cleaning off that water. So we did an experimental setup where we had this membrane system, this electrodialysis system here in the middle. We had a diluate reservoir that we pumped through. We had a concentrate reservoir that we could pump through. We had an electrode rinse reservoir that we could pump through. We put all kinds of monitors on there for flow and for pressure and for pH and conductivity and temperature. And it was a big apparatus. This is what it looked like. And the electrodialysis itself is a tiny little guy in the middle. And here are the reservoirs, and here's the monitors, and here's the computer system that ran the whole thing, and all work was being done in this little unit. Details, again, are not important to you. What is important is that it works. So the diluate, which is the water that we want, we can make the conductivity dramatically reduce over time, which would be the equivalent of passing through the membrane, passing through the electrodialysis system. And we're moving all the ions from the diluate into the concentrate, so the concentrate conductivity is good. And it's a function of how much electricity you supply to make that work. We also then could model mathematically what was going on in here. The details of this are way beyond what we need to talk about today. But in any case, the point is that we built a mathematical model to describe what's going on in here. And presto, we could model perfectly what's going on. The lines of the model and the data are the data points from the experimental things, and they basically fit almost perfectly. It turns out that I could show you some detailed slides and show it's not really quite so perfect, but nevertheless, very, very good model. So we think we know what's going on in this system. So my point of this is that desalination is a very possible way to increase the water supply that we have. It's not so simple, but it is quite feasible. And I try to indicate, what some of the issues and opportunities were in each of these 4 areas. The last thing I want to talk about, I just have really this slide on this, direct potable reuse of wastewater. That's so-called toilet to tap. Take your wastewater, treat it, and treat it really, really well, and make it into drinking water. And there's only 2 plants in the country that are doing this right now, and they're both in the state of Texas, and they're working fine, and it makes a lot of sense. Okay? But it takes a lot of treatment. And this is the treatment that we have. You take secondary wastewater treatment. You do it with nitrification, that's converting ammonia to nitrate. And then you do denitrification, converting that nitrate to nitrogen gas, which goes out into the atmosphere. And so, and then what this schematic, this is taken from a report to the Texas Water Development Board done by Alan Plummer and Associates. Anybody know Alan Plummer? Okay, so Alan is a graduate, PhD graduate of our program many years ago. Has a wastewater firm and mostly centered in Fort Worth and Dallas. But anyway, what this schematics is this. You do the secondary wastewater treatment, then you do an ozone treatment, then you do ultrafiltration to remove particles, then you do a reverse osmosis that we talked about to get rid of all the salts as well as many organic compounds. In case anything got through that, you do an advanced oxidation process to destroy any organic molecules that can still be left in the water. Then you do a post-treatment, because again, this is just like the post-treatment that we talked about in desalination. You possibly have some storage, and then you put it through a conventional water treatment process. And this is the way it's done in the 2 plants that are done. There's various minor adjustments that can be made in this, but virtually everybody is using reverse osmosis, and everybody is using some kind of oxidation process either before or after or both in what's going on.
So you do oxidation before and after?
Yes.
Afterwards.
Yes. Yeah. It's heavy duty stuff. And part of it is you want to make absolutely sure that you don't have a problem. Okay? And so there's redundancy built into this on virtually all the contaminants that you could possibly think about getting through. Because every industrial process occasionally has some excursion or whatever. So this is designed to make sure that even if something is a little bit wrong in some part, that it's not going to affect what the effluent quality is coming out. Yes.
Doctor, what about pharmaceutical waste and getting wastewater?
Yeah, that's, I'm doing work on that right now in my lab. I didn't talk about it here. But those will pretty much all be taken out in reverse osmosis because they're fairly large molecules and they don't pass through. And if they don't, there's likely to be dealt with in the ozone process or this advanced oxidation process here. So I don't think it would be a problem that to do that. And just to finish this up, I just want to say that last summer I published an op-ed piece that was published in numerous newspapers, and I'll be happy to send a copy of this to anybody who wants it. It's about this toilet to tap wastewater issue. And the main point I tried to make in there that the water that comes out of it is safe to drink. And perhaps it's even safer than conventional treatment in places where the water source is contaminated. And in the arid Southwest, many of our natural water sources are contaminated. So, for example, the city of Houston is drinking, Dallas's wastewater. Okay? The Trinity River is, in the middle of the summer, virtually 100% Dallas's wastewater. It travels, whatever that is, 150 miles, and then often Houston takes it as their drinking water source. And I guarantee you that they don't do the kind of treatment that I just talked about, and nearly as extensively. So my point in this op-ed piece was that toilet to tap, 4 places that have a contaminated drinking water source, which is many places in Texas, that the toilet to tap option is actually a better option. Which I have to tell you that 20 years ago, I never in my wildest dreams imagined that I would say that. But the technology has improved, the ability to monitor that technology has improved, and the natural water systems have gotten worse. And you put all those things together, and now I'm a believer that this is the way that we can go. Finally, I just wanted to comment that we have worries in Texas, but I wanted to just show you a couple slides about my PhD student, Ann Nicolonis, who's in the center here. This is a picture taken in Ghana just a couple of months ago. She's working on how to make drinking water in developing countries. And this is taken at a plant that makes these small pot filters, and they get coated with nanoparticle, silver nanoparticles. And silver is a great disinfectant. And as you pass water through these and collect it into a bucket, the silver disinfects the bacteria and viruses that are in that water. And you end up with much, much safer drinking water for having done that. And so this is actually from the research she did over there. They allowed her to use 15 of their pots that were done. She actually coated some of them herself with silver that she had brought with her from Austin. And in some cases used the ones that they had as well. And she tested what the water quality was for all of those things, and it turned out to make a big difference. And this is a picture that this home water supply company that supplies these things. This is a picture taken of a family, and here is their unit. And that clay pot is in the top here, and they pour water on the top, it goes through there, and then they end up with this small reservoir for their drinking water. So, water quality is totally essential. And, the women in this society sometimes walk for many, many miles per day to get really dirty water, to supply water for their family. They put it through these filters. And it's not nearly the water quality that we have, but it's way better than what they had before. And in the end, this is what drinking water supply is all about. So with that, I thank you very much. And remember that today is Earth Day. I hope you do something to conserve water today. So I'm happy to take some questions. Thank you very much. Yes, sir.
On the train of processes related to the reverse osmosis, what is happening to the bacteria and the viruses in that system?
Yeah, so the reason why we're using ozone up front is largely for disinfection purposes at that point. Okay, so we're doing disinfection here before we get to the RO. And then this advanced oxidation process would also kill any bacteria and viruses that are in that water at that point. And then, of course, in conventional treatment, we're going to add a disinfectant for the distribution system. So there's multiple ways in which microorganisms are accounted for in this system.
What is the output product related to the advanced oxygen or oxidation?
Advanced oxidation process. What is the?
In other words, is it ozone?
Oh, so what advanced oxidation means is that we're somehow producing hydroxyl radicals. Ozone can do that, but typically ozone in combination with ultraviolet light or ozone in combination with hydrogen peroxide is used to create the so-called advanced oxidation process. So it turns out that hydroxyl radicals are, highly oxidative, and so this is like the cat's meow of oxidation. And when people talk about somebody asked about pharmaceuticals, if people are talking about getting rid of pharmaceuticals in water, this is, the advanced oxidation is the way that they would talk about it. But they also, I don't think any bacteria can survive these processes.
Thank you.
Thank you.
What options do we have for waste management for the concentrations on inland desalination?
Oh yeah, that's a good question. So one option that's used that makes absolutely no sense to me whatsoever is to put it into a sewer and send it to the wastewater treatment plant plant, which does absolutely nothing to those salts, and is, I think, a ridiculous option. I think in the end, we have to evaporate that water or do deep well injection. And those are really the two options that have, make some environmental sense. And deep well injection is expensive, and you have to make sure you put it down into an aquifer that's already, highly salty, so that you're not destroying the moisture source. Talk to an oil company, that's right. They know how to do that. But one of the reasons why I think about reducing the amount of concentrate can make a big difference is that you can get the volume of the water low enough, especially in Texas, that you could think about evaporating the rest of the water. There are engineered evaporation systems that increase the rate of evaporation, and that becomes, and then you end up with salt. Unfortunately, one of the things that people have dreamed about is to try to end up with a useful product from that, but it's the separation of all the different ions is difficult, so it's unlikely. Well, it hasn't been solved yet.
Yeah, what were the two locations in Texas you used to?
Wichita Falls and Big Spring. Yes. Okay. Big Spring. And I haven't been to either of those plants yet. I know a fair amount about it. They use more or less this treatment scheme. What happened in both of those cases is that they were absolutely running out of water. I think the statistic for Wichita Falls was that the reservoir was down to 2.5% of its capacity when this plant came on. And I don't know what the statistic was at Big Spring, but it's similar. So it was dire circumstances that led to this. So I don't know. I think we should be proud of it. Texas is a leader in wastewater reuse. Yes,
You didn't mention anything about gray water.
I didn't mention anything about gray water. It's a good point. I already took more time than I was supposed to. Yeah, so there is a lot of interest and a lot of work going on, including in our department, about the use of gray water for irrigation and other things. Yeah, there's definitely an option to do that, and then it reduces how much drinking water you're using for the purposes that you're doing. So yeah, it should be on the list. I agree. Yes, sir.
You didn't mention anything about aquifer storage and recovery.
That's true. I did not, and it was on my first slide about indirect potable reuse, so the concept of that is very, very closely related to what I'm talking about here about direct potable reuse. The difference is that instead of this engineered storage here, you do a natural storage in a groundwater aquifer or perhaps in a surface water reservoir. And this has been used in California quite a bit, and it's used in Texas, I think in this area some as well. And it's a very good option. In a lot, treatment-wise, it's really not significantly different than this, although people think you can get away with a little less treatment because you have this natural buffer storage. And but I think of them as being very closely related. The biggest difference is public acceptability. People are, except in dire circumstances, not ready to accept the idea of toilet to tap. Whereas when you put this, instead of having engineered storage, you put natural storage or so-called environmental buffer in there, people seem much more willing to accept that it's fine water. In both cases, I think it's fine water. Yeah, that's right. I stand corrected. Anybody else?
Does Middle also treat some of the wastewater?
So So El Paso is in the midst of investigating this possibility, but they're not doing it yet. So El Paso is a leader in the desalination. They're using brackish groundwater as their water supply. They have, when it was built several, 5 or 8 years ago, the largest desalination plant in the U.S. for brackish groundwater. And they are investigating now the possibility of using direct portable reuse of wastewater. And in fact, the design is going on. I'm very familiar with that because they've asked the National Water Resources Institute to kind of provide some guidance to their, kind of between their design engineers and the utilities, kind of have somebody else look at that whole system and make sure that it makes sense and whatever. And I'm one of the people on that, so I know a lot of details on that. But it's not approved yet, it's not even decided yet, but they are definitely heading in that way. Interesting thing, I've been to El Paso 4 days in the past year for this reason, and it's rained all 4 days.
You need to keep going.
Anybody else? Well, thank you so much, and thanks for being great graduates of our program.
I'll just say a couple of more things. Hopefully you're proud of the fact that you heard Des say probably 10 times in his presentation that we are working on these problems. So hopefully that makes you proud that there are faculty and undergraduate students and graduate students that are working towards helping to keep water flowing in Texas. So thanks to the environmental engineering group for that. And I wanted to say one more time, thanks to Peyton Dawson for making these wonderful new facilities available to us today. Oh, and it's actually reminding me of a third thing. So in front of you, you should see a card. And in front of your card, thank you. A card that says one word on it. What we've been doing is asking alumni to write down one word that exemplifies or defines what your educational experience at the University of Texas meant to you. There's one caution, is that if you write down that word and you write down your name on here, it can end up on our website. So if you go to our website, you'll see that a large number of our alumni have put down one word and a sentence about what their educational experience meant to them in our department. I hope you'll do that, but that's the caveat.